This is the last of a 7-video series on factoring, sum and difference of cubes. Before we can get to the actual factoring, let's talk about what a cube is. Of course, a cube is a shape in geometry, but when we say cube in algebra, we are not referring to any shapes. Here's an example. 125 is called a cube because it is equal to 5 cubed, or 5 times 5 times 5. In other words, if something can be expressed as something times itself, then we call that thing a cube. X to the 21st power is a cube because it's expressible as 3 factors of x to the 7th. 8x cubed is a cube because it's writable as 2x times 2x times 2x. And likewise, 27 is a cube since it's 3 cubed. So let's take 2 cubes from that list, 8x cubed and 27, both of which are cubes, and let's put a minus sign between them. That makes this a difference of cubes. And that's what we're going to learn how to factor in this video. Okay, there are 2 strategies. One of them involves a formula. And it's called the difference of cubes formula, and I've put it here for you. And I'm going to show you how to use this formula, but at the same time it can be a little confusing, so if you find yourself getting lost in this explanation, don't worry. There'll be a different explanation that does not involve this formula that many students like better. But if you're a formula person, here's what you can do. Consider the left side of this formula as the problem we're factoring, and the right side as the answer to the factorization. Now, of course, there's no a's or b's in our problem, but here's what we can do. We can compare the problem to the left side of the formula, and we can ask the question, how are we going to find a and b to fill in this formula? Well, if you look what appears in red, the only way that those 2 things can be equal is if a were 2x. Now, before I go any further, this is logic that escapes many people. And if this doesn't sound like the way you think, don't worry, there's an alternative method right after this one for the same problem. But if you're comfortable with this kind of thinking, the same logic applies to what you see here in blue. What could b be in order for those 2 blue things to be equal? Well, since 3 cubed is 27, b would have to be 3. And now my plan, everywhere I see an a in the formula, I'm going to put a 2x. And everywhere I see a b, I'm going to put a 3. Watch as I do this. Here's the general structure of the formula. Everywhere I see an a, I'm going to put a 2x. Here's an a. I'm going to put a 2x there. Here is an a squared. A squared means a times a, or 2x times 2x, which works out to be 4x squared. There's where that came from. Here's another a becomes 2x. Alright, done with my a's, but I also deduced that b would have to be 3 for this formula to work. So, here's 2 b's, each of them becomes a 3. And here's a b squared, which becomes a 3 squared, which of course is 9. And now I'm done with my b's. Well, that's pretty much it, except for this one term right here. It's the only simplifiable term in the whole problem. That obviously works out to 6x. Everything else stays the same, and that is our factorization. Problem and answer. Now I'm going to show you a second way to do this problem, but before I do, consider the following. If this is the answer to this problem, wouldn't it be the case that if I multiplied all this out just like we learned in polynomial multiplication. Wouldn't all of this multiply out and simplify to the original problem? Well, how could all this complication simplify to something so small? Watch and you'll see. As we go term by term here, 2x times 4x squared, this times this times that. In other words, as we go through the normal multiplication process, and I won't read everything out here, but if you need to pause the video, now would be a good time to verify that this is what it in fact works out to. Once you've done that, you'll notice in the simplification process, this is the only x cubed term, so that appears in the answer. These two terms cancel each other out, as do these. And so the minus 27, which does not combine with anything, also carries into the answer. And we see, in fact, that this product of a binomial and a trinomial, this big ugly thing in the middle of the screen, does in fact multiply out to be the original problem. Now when you're factoring, you don't have to multiply your answer out to see if you get the problem back, but it wouldn't hurt as a means of A, teaching yourself what factoring is, and B, just a way to check your answer to make sure you didn't do anything wrong. Now, same problem, take two. That formula with the A's and B's, some students find that immensely frustrating. It's something about extra letters being introduced into the problem that just sort of sends the brain off into a place that it doesn't come back from. And so I'm going to show you an alternative method that you can use without using any A's or B's. But in order to do so, you have to literally memorize this shape that just appeared in the center of your screen. The dots are times, and that's essentially the formula that I used that had the A's and the B's in it. But now I'm going to do the same thing without any A or any B references. Here's what you do. It's essentially the same, but it has a different look. You do something called a cube root. You cube root the term in the beginning of the problem, and when I say that, I mean what cubed would equal that? In other words, what times itself would equal 8x cubed? Well, guess and check will bring you to 2x times 2x times 2x would equal that. And so the cube root of 8x cubed is 2x. Similarly, we cube root the 27, meaning what times itself would equal 27. And after a little thought, you'll realize that that would be 3. Now, once you have the two cube roots, you have to put those cube roots, you have to put the red and the blue thing into the formula. Now, here's the one disadvantage about not having any A's or B's around in this problem. You have to remember where the cube root of the first term goes, because it goes 4 places, and where the cube root of the second term goes, it also goes 4 places. That's kind of why the A and the B are in the formula in the first place, to remind us what goes where. But technically you can get away without using the other letters, as long as you remember where everything goes and you remember the structure of the problem. At this point, it's just a matter of simplifying, because you've essentially factored. The first factor stays the same, there's nothing to simplify there, but if you look at the second factor, you'll realize there are some multiplications that we could do. So you work this out, that's of course 4x squared. You work this out, which is of course 6x, and as we all know, 3 times 3 is 9. And notice, I've done this entire problem. Here's the problem, here's the answer. I've done the whole thing without ever mentioning A or B. If that's the way that it fits into your mind best, then do it that way and avoid the difference of cubes formula. There's also something called a sum of cubes. Here's an example of a sum of cubes. It just means that there's a plus sign or a sum between two cubes. Now I could do this using the sum of cubes formula, and this is almost the same as the difference of cubes formula with just a few signs changed. If you compare them side by side, you'll notice that. I'm not a big fan of the formula. I kind of like the second method, where I just memorize that format right there that you see in the center of your screen, and just use the cube roots inserted into strategic places. Alright, cube root time. The cube root of y to the sixth. That means what times itself again would equal y to the sixth. Well, y squared times y squared times y squared is y to the sixth, so there's my cube root of the first term. Now the cube root of 125m cubed. Well, it takes a little guess and check sometimes. 125 may seem like a strangely placed number to you, but 125 is a very unique number because it's 5 times 5 times 5, if you were to work it out. And there's no way to know that other than just trial and error. But after enough thinking and guessing, you'll deduce that the cube root of 125m cubed is 5m. And you can imagine how 5m times 5m times 5m would equal that. Well, now that I have my cube roots, I just have to put them into the 8 slots in this formula. There's where the first cube root goes in those 4 slots, and here's where the second cube root goes in those 4 slots. And once you've done that, it's just a matter of leaving the first factor alone and simplifying the second, which isn't too much work. Just do the multiplications. Y squared times y squared, there's that. Y squared times 5m, I could leave it as y squared 5m. I like to write things without exponents first, doesn't matter. And 5m times 5m is 25m squared. And as messy as that is, this is a pretty simple way to factor a sum or difference of cubes. There's your problem, there's your answer. And that completes the 7th of 7 lessons and this series on factoring.